It's not.
Okay, so our next speaker of the session will be Marie Braasch from the University of Vienna, who will talk about second harmonic generation to enhance the performance of diffractive neural networks. So please, Marie, go ahead.
And was this one? Okay. Yeah, okay. Welcome to my talk about second harmonic generation in all optical diffractive neural networks. I'm a PhD student in the Friedrich University of Vienna at the Institute of Applied Physics. Yeah, actually, I enjoyed all talks very much, but the first one prompted me to add this slide because, well, we're doing all the wrong things. So first the question, 2D or not 2D. So our system is not 2D because we're doing diffractive neural networks. Then power efficiency or accuracy. We are using second harmonic generation, which is not a very efficient process. So also failed this. Fixed or adaptive? Well, once in a while one has also to be right. So our system is fixed. And analog, OEO, or all optical, well, we are trying, as the title suggests, to find an all optical solution. So here we failed again. But actually we are not the first people who thought about using SHG in diffractive neural networks. So there's this other group who use SHG in the depleted regime, where they achieve actually to model a ReLU function with these waveguides. It's a very interesting paper, you can have a look. And also very interesting is that the input frequency is also the output frequency, so this kind of gets rid of the problem that we always, if one would like to cascade these systems, that the frequency always gets larger and larger. But we are working in the undepleted regime, and our concept, or what we tested, is basically the conditions under which SHG gives us a benefit. And we have an amplitude encoded input, then we Fourier transform that onto a series of linear layers, and somewhere in there, or the end, comes our nonlinear crystal, and then we have another Fourier transform to the output plane. So I will skip mostly over this method slides because all of you are already experts. But maybe interesting is that we are using cross entropy as a loss function, which prefers accuracy over contrast. And we have 56 by 56 neurons per layer, so just that you get an idea about this size. So next, to give a fair comparison of all the models, we optimize the hyperparameters. Most importantly in our setup is actually like the size of the face mask right after the first Fourier transform, because you can already see that here everything is very sparse, so it actually has to be quite small to give us a benefit, and also the size of the detector at the output layer. And for this, we use a Bayesian optimization algorithm. So now let's get to the results. So in particular, we tested different configurations, and we looked where to place the nonlinear crystal to get a benefit. So intuitively, in the beginning, we thought, well, the easiest thing for first experimental realization would be to put the crystal right at the face mask, maybe even in a joint system, so we don't need any extra more lenses or anything. But the first simulations showed immediately that for these configurations, the accuracy is actually worse than for a system with a linear layer. And well, this depends on the data set, but for all the data sets we tested, this was true, but in general, it is definitely preferred to have this face mask to model the mixing before we get the crystal. Also very interesting is if one writes down these equations of the squaring of the field and this phase modulation, actually the operations are exchangeable if the face mask is adapted accordingly. So just by a factor of 2, then these systems are actually the same. So if the question ever comes up, if we want to place a crystal before or after the layer, it doesn't matter so much, but it does affect the training a little bit. That's why you see the difference. And however, if we put this after some propagation, then we see immediately an increase in accuracy, and this is around 3%. And also what we see is that the class contrast is improved for all the systems which include SHG, which is very desirable because we do not have these high efficiencies. The class contrast I define as the intensity in the correct patch divided by all the other intensities in the other detection patches. And here we can see the intensity at the detection plane for the different configurations, and I think we can clearly see that for this position 3 setup, actually we get a much better output, which is relevant in experiment, because if we have just a blurred image, it won't be measurable. So actually, even though the efficiency is lower, it will be more robust because we can distinguish where the patches are actually on our detector. So here I just support this with different data sets, the fashion and MNIST data set, and everywhere we see that we have this contrast improvement of nearly here a factor of 2 for the digit, fashion a little bit less, and for the MNIST it's only slightly. And for the accuracy, we also get a consistent improvement for the setup. So I also tested more configurations here, a multi-layer, and again we see this trend that the accuracy drops if we have it at the first layer. So this is just one crystal, at this position. And then if we have at least one layer with propagation, then we get this improvement. So finally, the question always comes up: how efficient is this actually? Can we even measure a signal? And so one thing I did not mention so far is that we model the field in our simulations by just taking the input field and squaring it. So we assume that within this nonlinear crystal, there's no transverse mixing, no diffraction. This is, of course, only true if the crystal is short enough. And so what we did is, under these assumptions, see if we get enough signal out. So basically, we take the crystal and we look at the field in the beginning of the crystal, and we sample the field by a range or some Gaussian beams, which have a radius equal to the feature size of that beam, which we choose for simplicity of the size of the features in our phase mask. And then we know that there is no transverse mixing if, for these Gaussian beams, the Rayleigh length is much shorter than the crystal length. And this is what we introduced this factor B, which gives us a level of approximation. So the higher B, the better our approximation. And if we take the equation for the conversion efficiency and introduce these considerations, then we end up with a conversion efficiency that is proportional to the crystal length, opposed to the square of the crystal length. And also, the better our approximation gets, the worse the efficiency. So here we then see the output power of the second harmonic given an input power of 1 watt over the crystal length and feature size. And here I picked just one line with a factor of 5 for the approximation quality, which is, if we test it with rigorous simulations, okay. And here I now picked this value and computed the SNR for just some CMOS camera with it has a good quantum efficiency, so we operate at 532 nanometer. And so if I plug in all the considerations and patch sizes and these numbers, then I end up with an SNR of 42.5 decibel, which is good. So, and this is only for an input power of 1 watt. So one can scale this up, one can use pulsed lasers. So this should be in the range of possible and detectable. So where is this research heading? So now we're working on a real physical experimental setup. So this was all numerical work only, but now we are working in collaboration with Giuseppe Leo's group, who have these meta surfaces that for enhanced SHG, including phase control, so it can do both. And Anna is working on this, and she also has a poster here, so you can have a look later. And so we have there, the idea is to have one linear layer, so one phase mask, and then this joint system. And she also has results for the spiral data set on her poster. And this is one of those examples where the data set is much better suited for the nonlinearity we are using here. So that actually the improvement in accuracy is about 20%. So yeah, I think this was my talk. Thank you for your attention. And here is like a preprint of all the results you've seen today, an archive. And then I also included like for this popular science article where we give an introduction to DNNs in case you are not so much familiar with it yet. And there we just have a little comparison or the classification problem of distinguishing a mob from a dog, which is hard. Yeah.
Time for questions.
Yes. I must confess that even my own papers of current research in the university, they're also I fail almost all of them. So, yeah. But very nice work. I really appreciate it. So the idea is just a square law, right?
And
the nonlinearity is just a square.
It's just a square, yeah.
The middle, right? And then you get the second square at the output, or no?
Exactly, yeah.
I was wondering if you could use chi3 and use difference, or if you use chi3, you can have two.
One could probably use that. We did not test it yet, but of course, second harmonic generation is also one of the most efficient parametric nonlinear processes, which is why we chose
chi3. Right?
Yeah, I think so. Yeah. Okay, maybe I'm wrong. I'm sorry.
Yeah, but you need a second one.
Yeah. Yeah. Okay.
More questions for our speaker? No more questions? Please.
So there are a lot of different kinds of optical nonlinearities you could have used, like maybe saturable absorption or the Kerr effect. Is there a reason that you chose second harmonic generation in particular?
Well, the reason is first off efficiency, and also we are very experienced actually in our group to do second harmonic generation, and there's these phase masks or meta surfaces that do both, so that was mostly the reason, yeah. But we also, like, not me in particular, but Frank also looked into saturable absorption, so I'm not sure, do you have a post? Yeah, so maybe you can also, yeah.
Any more questions? Okay, I have a question from my side. I did not fully understand what's the mechanism that causes the accuracy to degrade when you add only one layer of nonlinearity. Do you have an understanding why does this happen?
So basically, this is not generally always happening. It doesn't need to be. It really depends on the data set. But in the end, you're just transforming the input to something else. In our case, I'm sorry. I ended it. I was thinking about why it happens in our case. And I think one can imagine if this is our field intensity, if we square this, it becomes even more sparse, and it's not very a good problem here. But yeah, there could be cases where it's actually beneficial. Yeah.
Thank you very much. So let's thank our speaker, and now we have a coffee break. Come here in 30 minutes at 35.